Okay, awesome. So I think then we can kick off our talk today. I'm like really excited to have you because, every month we have our happy hours, and Mihai, one of the members who always come to those meetups, and we have like really great and fun conversations. And I asked like who you would love to come to give a talk in our meetups, and one of our community members mentioned about you, and they're like really love what you're doing, and like super excited about your work, and that's why I really wanted you to come and share your thoughts with our community. For those who are first time in our meetups, welcome to our community. I will share a link to our Slack where we hang out, and in general, my goal is to facilitate supportive environment and help each other. Let's say if you are working on some technical projects and you're stuck and you need some help, you always can, share your technical requests there. And in general, like this is basically like, community of like-minded people who do machine learning and data science, and in general think about what is cognition, what is intelligence. And today, Joscha, our guest, will talk about this. And just a couple of words about our speaker, Joscha Bach, who is a principal scientist at Intel, and also his research involves like computational models of cognition and neuro-symbolic AI. And maybe Joscha, you can dig more deeply in your research.
Thank you, Sophia. Yes, I'm basically a cognitive scientist. Most of my work in the past has been in the field of cognitive architectures, where I try to understand the relationship between perception, motivation, and cognition. And at the moment, I am working at Intel Labs in a group that is trying to figure out what comes in the future of AI and how to evaluate future AI systems and understand qualitatively and quantitatively how we can understand and assess the dimensions in which they exhibit performance. Today is going to be a slightly more philosophical talk. And AI is, as many of us are aware of, not just a field that is automating statistics, but originally it has also been a philosophical project. And as philosophical projects go, it's a relatively large one. It involves, I would say, a few thousand people. And it's a very risky project. And this project, it's also the most interesting and I think most relevant one that exists in the history of philosophy. And of course, it's only a very, very small fraction of what our field is doing. Like, most of our field is working in engineering. And a lot of confusion emerges because people are confusing AI as a philosophical project with AI as the engineering project. And today I'm going to talk a little bit about the philosophical project. Philosophy itself can be understood as the realm of all theories, where we explore everything that can possibly be true. And philosophy is largely done in natural language, and natural language is not very well defined. So it's very hard to say something in natural language about the complicated questions of philosophy that is true, because natural languages are so ambiguous and heterogeneous and have to deal with a world that is not very well described by natural language ultimately. And it's tempting to start out from mathematics to philosophy. And mathematics can be understood as the realm of all the languages, not just the natural languages. And here what we are most interested in are the formal ones, the most simple ones. And in these formal languages, we can say things that are true because we define truth formally in mathematics. So we get to a very narrow, clear understanding for what it means for a statement to be true. But the problem with mathematics is that it's very hard in mathematics because it's so simple to say something interesting about the world that we are in. And it's very hard to say a mathematical sentence about our experience of the world or about what we care about and so on. And about the question of what is meaning, how are we embedded in the universe, what is agency, and so on. And formalizing these terms is something that is so difficult that mathematicians, for the most part, haven't even started going there. So the question is, how can these two realms meet? And it probably means that we have to automate the thing in between mathematics and philosophy, which is the mind. Right? If we can mathematize the mind, if we can mathematize the systems that are able to form theories, and we have to do this by making them autonomous and self-organizing to, in some sense, replicate the structures that our own mind is producing. So we can say things in mathematics that are true by building a machine that is making these proofs and explores them and so on, that is basically taking over from us. We will have a way to prove our theories about the world. And a big step in the last century was that we discovered that mathematics is some kind of code base that has been developed over a few thousand years. And some of the assumptions in that code base had been wrong, especially the way in which truth was defined. And that is a big implication of the work of Gödel and Turing. What they discovered is that we cannot build a machine in the language of mathematics, that in any kind of mathematics that runs the semantics of the existing mathematics without breaking. Basically, what Gödel and Turing discovered is when you assume that the existing semantics of mathematics are true, you run into contradictions. It was a very big shock, especially to Gödel, who strongly believed that truth, as it was commonly understood, was actually the true truth. And what Turing discovered was we can actually build a different machine, a computational machine. And this computational machine is able to recover all the semantics that mathematicians were using in practice. What you're losing is infinities, continuity, and a few other nice things. But there is no infinity and continuity that mathematicians are ever working with. Continuity is just too many parts to count in the physical universe. Right? So when you have too many parts to count, you have to find operators that are converging. And the operators that are converging in the limit over too many parts to count, this is geometry. So now we have a new perspective, a computational perspective on everything. And this computational perspective already existed within mathematics. It was called constructive mathematics. It's the part that actually works. So we could say that AI as a philosophical project has as its goal to unify mathematics and philosophy using computational models of the mind. You could also look at it in a different way. It is basically exploring the question of what intelligence is. What is it that the mind is doing when it's making models? And if you're able to succeed in this task of building a system that is able to make models in the same way as we do it, then what we are building is a system that is able to understand how minds work. So in some sense, the goal of the Turing test should be to build a system that you can ask how it works. Right? If it's able to explain to you how a mind works and how you work, you have succeeded. And in some sense, this Turing test you're performing on such a system is you build a system that is also able to perform Turing tests on you and on itself. And that system is able to explain to you what it is. And the question that Turing is also trying to answer in this way is Turing generally intelligent? Is Turing able to explain how a mind works by building one? AI is a philosophical project in a formal sense, started quite early, maybe with Leibniz, who had this idea that we can build a calculus that is describing everything in the world, and then we can just calculate the answer. And my own philosophy teachers had been very dismissive of this project. How could you turn everything into numbers and then do calculations? What a naive idea. And I don't think it was that naive at all. It was actually this idea of building a machine that can perform these calculations. And this universal calculus is something that has kept a lot of people busy, like Frege with the Begriffskalkül and so on. And in the last century, the most prominent start into this was arguably Ludwig Wittgenstein, who had this idea of formalizing the language that philosophers are using by basically making English much more formal and strict. It's a very beautiful idea. And this idea of turning English into a programming language for thought is expressed in the Tractatus Logico-Philosophicus that he wrote as a young man coming back from World War I. It's a very beautiful book because it is not tainted by footnotes and references and arguments. It's just a very clear elaboration of this particular thought, but you can understand it best if you had this thought by yourself. It's not trying to convince anybody. He also makes that point and explains that it's basically not trying to make an argument that is convincing other philosophers. It is an idea to write down a particular thought that you will understand after you had it. And so it's a book that can be understood, I think, quite well by somebody who is a programmer, who has thought about writing a language for thought. But it's a book that endlessly confused philosophers in the last century because they didn't know what he really meant. And in his remarkable book, he preempts Minsky's logicist project, the idea of writing a language in which you can do AI by several decades, and also its failure, because at the end of his life, he concludes that it didn't really work because he was not able to integrate perception, or as he mentioned, pictures or images into his formal language. And this was something that is only now happening with deep learning, where we are developing automatic function approximators that can deal with perceptual content and integrate this into the formal models that we are building. So Wittgenstein couldn't see this yet, but Turing was one of his pupils, and you know how that went. Classical AI is mostly symbolic, and classical AI was the stuff that in this very simplistic and clear, not as clear-cut distinction in practice, but the idea was that you analyze a problem, you find an algorithm to solve it. And the easiest example is chess. All the early chess programs were written in a way where the developers thought about how can we find an automatic strategy to play chess, and then let's implement the strategy and make it fast and efficient enough, optimize it enough so it can beat human players. And currently we are in a different era of AI. It's this deep learning era. It's mostly sub-symbolic, where we don't write the solution to the problem, but we write an algorithm that learns the solution to the problem, that discovers the solution to the problem by itself. And it's tempting to think that the next era of AI will be about meta-learning. So we don't write algorithms that discover the solution to a problem, but algorithms that discover how to discover the solution to the problem, that learn how to learn. At the moment, we are using mostly neural networks, and the neural network is a chain of weighted sums of real numbers. And the weights in this network are changed with various algorithms, mostly stochastic gradient descent. And there are many alternatives to neural networks, so it's not the only way. The entire goal is to make compositional function approximation. And the thing that works best in practice for many of the tasks that we have picked is stochastic gradient descent, which means in some sense differentiable programming. And the main paradigm for that is still Frank Rosenblatt's perceptron from 1958, and he was not the only one who discovered it. And back then in his work, he didn't discover backpropagation yet, even though he could already see what would need to happen to make it, to pull it off. Minsky and Puppet delivered a formal proof that the perceptron learning algorithm that existed in Frank Rosenblatt's perceptron was not able to learn XOR, and by extension, many, many other functions. And so this book by Minsky and Puppet, which they wrote to point out that we would need more complicated systems. Minsky preferred to make systems that are more proposition-based, language-based, knowledge-based. Stopped research on neural networks and funding, especially on not the research, but the large-scale funding for more than a decade, and delayed the development of connectionist systems. But in some sense, this has never stopped. And at the moment, it's the most successful paradigm in AI, arguably. And what we find is that there are no longer black boxes. If you look at DistilPub, the excellent work by Chris Oler's team at OpenAI, it's possible to analyze what these networks are doing. His hypothesis is that features are the fundamental unit of neural networks, and they correspond to directions in an embedding space. And the features are connected by weights and form circuits. And that there is a universality condition, which means that analogous features and circuits will form in different models if you give them similar tasks, and the model is flexible enough. But these artificial neurons are very, very different from biological neurons, which are self-organizing. Biological neurons are basically all little animals. Each neuron is a little animal. And this little animal tries to survive. And to survive, it needs to get fed. And it will get fed if it does the right thing from the perspective of the surrounding organism. And the right thing is that it needs to fire at the right moment. So every neuron has to learn when to fire based on its current environment. And the current environment is, from the perspective of the neuron, a certain electrical and chemical configuration of the environment. So it has to figure out which signals in its environment signal that they should fire. And the neuron will put tendrils into the world to make that measurement, to figure out when it should fire. And there are different types of neurons that have different biases in their strategy to explore the space of possible solutions to the questions of when it should fire. And they form an organization. They have a shared destiny. They're all locked together in the same dark skull. And the only way that they can survive is that they collaborate in a way and together give each other feedback on when they should fire. Right. And we know what the overall result is. You get this emergent structure in it that from the outside or from a certain distance looks like there is a common spirit that is evolving in the coherent patterns of the firing of the neurons, this virtual thing that we call a mind. And for me, it was a very big insight to realize that the word spirit is not a superstition, but that spirit is basically an operating system for an autonomous robot. And when the word spirit was invented, the only autonomous robots were known were not built by people, of course. There were people themselves and other organisms like plants and animals, and there were ecosystems and cities and nation states. All these systems basically have emergent virtual software that you can project into the coherent functioning of their elements to make them explainable. So in some sense, you get a system from the organized coherent activity of its parts that behaves as if it was following a shared telos, a shared purpose, a shared structure, a shared computational strategy, and could be described with a single software. But what is it aiming at? And Carl Friston says what it's aiming at is the minimization of free energy. And what is meant here is not some thermodynamic energy, but you can use an energy description to describe the state of the system that is modeling its environment. And that energy is minimized when the system needs less energy to update in the next state. And so the idea here is that the system, whether it's a brain or a cell, is modeling its entanglement with the environment in its own internal state, and it's trying to minimize the prediction error. And we now have to understand how to do this in a self-organizing system. Technological systems like neural networks use a functional design. We think about what does the individual representational unit need to do, and then we impose that function on it. And it just does it because we build it on a completely deterministic substrate. Our computers are designed to be more or less completely deterministic and follow the rules that we give them and don't deviate from this ever. And biological systems or social systems are not like this. Here we need a meta design. We need to design them in such a way that they want to converge to the desired functionality. Right. So instead of building a FDA that is following a set of rules and then it's gatekeeping the access to medications in such a way that people don't poison themselves and so on. If you just implement these rules, it's not going to work, because after a couple of generations, the FDA is going to be captured by the producers of medication and is acting as a gatekeeper against innovation that would prevent new, better, cheaper medication to enter the system. And eventually it's going to also limit the access of people to completely safe medication that doesn't have patents on it, so nobody makes a profit on it, right? So if you want to prevent the capturing of regulators of other social systems, you will need to design them in such a way that they want to do the right thing. And if you cannot do that, you need to make them mortal. You need to make sure that they die every generation and get replaced by a fresh system. Maybe we should think about how to make mortal institutions that die after a certain time so they can rejuvenate and rebuild. Anyway, biological neurons are not just functional approximators, they are agents. How can we understand what an agent is? And here, what helps us is to use cybernetics. In cybernetics, we can start to define what it means to be motivated. And the core of cybernetics is, as we all know, the feedback loop. And a feedback loop, if we want to turn this into an agent, we take a controller. The controller is connected to a system that it regulates via effectors, something that can change the state of the regulated system, and sensors. And the sensors measure a set point deviation, a deviation from how the regulated system should be. And the controller is now implementing a model that tells it how to go from the measured set point deviation to a change in the effectors that affect the regulated system. And the regulated system goes out of whack again and again because it's being disturbed by the environment. And the better the controller is able to model these disturbances, the better it's going to be able to deal with the set point deviations over a long time span. In the simple case, you have a thermostat that is only optimizing for the next moment, for the next frame of the system. But if you have a system like us, we're able to optimize for an integral over the set point deviations over a long time span. And to do this, we need to model the future. And if the controller is able to model the future and the structure of the environment, then it's going to distinguish between situations that it prefers over other situations, and it's going to implement strategies on how to get to the situation that it wants. And when we describe the system from the outside, we will attribute agency to it, because this is what an agent is. It's a controller combined with a set point generator that is able to act on something that it regulates while modeling the future of that regulated system and acting on the model of that future. And the good regulator theorem states that every good regulator of a system must be a model of that system, or must implement a model of that system, which also means that you cannot model the world efficiently if you don't make a truthful model of it. Right? So when you, for instance, try to build a more just world, it doesn't help if you use categories that don't model the world as it is, but as you want it to be. That is not going to lead to the best possible regulation. If you lie to yourself about the true state of the world, your regulation is going to be off. So if you want to model the world, if you want to improve the world, if you want to control something, regulate in the right direction, you need to start with a complete service to truth. And you need to come to a description of the system that you want to regulate that is isomorphic to the dynamics of that system at the level where you want to regulate it. And the universe that we find ourselves to be in can be understood as a universe that can be controlled. And I think that's the answer to this big conundrum. Why is it possible that we can learn anything at all? Why is it possible that we can recognize structure in the universe? Why are we in a universe that is intelligible? It's because we are controllers. We are on top of a hierarchy of control systems. So in a way, you could say that elementary particles are controlled zero-point fluctuations. The atoms are controlled elementary particles, and molecules are controlled particles, and cells are controlled molecules, and organisms are controlled cells, and societies are controlled organisms, and so on. Right? So we have a hierarchy of control, and because this to control, you need to make a model of the underlying system. It means that a controllable universe is also one that can be modeled. And the models that an atom needs to make of the elementary particles, of course, extremely simple, because it's an extremely simple mechanical regulation. But the models that a cell needs to make to control the molecules that make up the cell are very, very complicated. And there is something like a shift in the complexity. And that shift in the complexity means that the cell, in order to enact this regulation of the molecules, needs to implement a Turing machine. It needs to be a computer. If the cell cannot compute, it's not complicated enough to learn how to model the future of these molecules well enough to build this giant supermolecule, the cell with all its dynamics, that is able to withstand many, many types of disturbances in the universe. So the purpose of all this regulation is to maintain complexity, to build systems that are stable against disturbances, are self-propagating when you disturb them over a larger range of environments. We can ask ourselves, is the universe a computer? And isn't it a dynamical system? And the answer to this is that, well, there is no true continuity for mathematical reasons, because if you want to talk about infinity in any kind of language, you will run at some point into contradictions if you try to explain how that works, which means that your word don't mean anything anymore, right? If the language in which you try to talk about the world falls apart, it means that the words lose their meaning. You cannot actually talk about infinity without presupposing that you already know what you're talking about. And so we can replace that notion of infinity by too many parts to count. And then we get all the same things that we wanted without the contradictions. And the world that we are in is one that is made of too many parts to count. So the dynamical systems that we use to describe the world are the same as before, but they turn out to be computational systems. Vice versa, the computers that we built to describe the universe are built on top of dynamical systems, and we basically stack the probabilities of these systems until they become deterministic enough for our purposes. But another question you might ask is, are quantum systems computational systems? Or are they hypercomputers? Aren't quantum systems able to compute things that classical computers cannot? And well, if you look at what a computer is, if you look at the Church-Turing thesis, a computer is in some sense a system that is able to go from state to state in a non-random fashion. It doesn't get much more general than that. And the quantum system is also nothing but that, right? A quantum system is characterized by a state that is a superposition of possible states from a certain angle, but it's still a state. And then you have a transition between them to the next state. And so a quantum computer is also just a computer. But the reason why quantum computers can do things that particle computers cannot is that, according to quantum mechanics, the particle universe is very inefficiently implemented on top of the quantum substrate. Right? If you are implementing a computer in Minecraft from redstone, you can do that. There is going to be a polynomial time relationship between the speed of the computer that you implement within Minecraft and the CPU that Minecraft runs on. Of course, the computer that runs is inside of Minecraft is going to be much, much slower than the computer that Minecraft runs on, because most of the computations of the computer that Minecraft runs on will not go into the computations of the computer that you built within Minecraft, right? So your simulated game world computer is going to use only a fraction of the computational resources. But according to quantum mechanics, the particle universe is so inefficiently implemented on top of the quantum universe that the quantum universe is branching off in many, many ways. And most of the computations of the quantum universe are not contributing to our timeline. And so it's only a very small fraction that drips into the available timeline. And quantum computers are basically the bold hypothesis that we can tap into our quantum CPU and the quantum substrate that the particle universe runs on, and use some of the additional computations that are not available to the particle universe to drive the computations that we want. So quantum mechanics is also not a hypercomputational notion. Hypercomputation is it's another one that we could take a causal hypercomputation. Imagine we could build a closed time-lag loop. That means, for instance, we can somehow look into the future and get the lottery numbers of next week and use them now to win the lottery, right? This would be something that is not possible in a computer, right? Well, of course it is possible. You just back up the state of the present universe, right? You make a copy of the universe right now, buffer it, then you run the universe to next week, take the lottery numbers, store them, reboot the universe from the state that you have in the buffer, and then pass the numbers in. Right, so as long as you're able to memorize the state of the present universe, you're good. You can also build closed time-lag loops in a classical computer. So there is, in some sense, no way to get out of this. And we can ask ourselves, is there something about consciousness that requires us to move away? And I don't think there is something about consciousness that is very special. The issue with consciousness is very confusing because we think that our consciousness gives us access to the physical universe, and what our consciousness is perceiving is the real world. But it's not. Consciousness is a dream state. It's the state inside of a model. It's something like a multimedia story that is being generated inside of the agent. Physical systems cannot be conscious. Neurons cannot be conscious. Computers cannot be conscious. Consciousness is an entirely virtual property. Consciousness is as if. And because we live in this as if world, we can perceive things as real, because being in a physical world, being in a computer doesn't feel like anything. Right? Some people think that computers cannot be conscious, that simulations cannot be conscious, but they have it backwards. You can only be conscious in a simulation because it's a simulated property, not a real one. It cannot be real. And then there's this big question of existence. How is it possible that something exists at all? And to this one, it looks very unsatisfying from the perspective of a computationalist. And the easiest answer that I found so far is that maybe existence is the default, right? So rather than assuming that you need to add something to the universe to call something into existence, the universe is already the superposition of all the things that could exist. And if for something to exist, it must be implementable. I think a good definition for existence is implementation. Something exists if it's implemented. And everything that's implementable are finite automata. So maybe the universe is a superposition of all finite automata. And the structure of the universe is the result of those things that don't exist in the superposition of all finite automata. Basically, the wakes of certain operators that create gaps in existence. So maybe the universe, after all, is something like an inverse computer. It's a superposition of all the operators. And if you superimpose all the operators, there's still going to be some states that are not attainable. And this gives the structure to the universe. But I don't know whether that's true. That's extremely speculative. I don't have an answer to the conundrum why something exists at all, which is the one that really shocks me. That is satisfying to me. Anyway, let's go back to agency. We pointed out that to generalize control, we take this control model. The controller minimizes set point deviation. The minimization of the future set point deviation requires the controller to make a model. And the model has to predict the result of the interaction. It has to make something like causal model. And an agent is a controller combined with a set point generator. And the controller needs to be able to model the future and has preferred states. And I would say that a sentient agent is one that is discovering itself in this interaction with the world, right? So once you discover your own agency and that you discover that there is a system that is changing the world in a particular way, and that system is using the contents of your own control model, you discover your own first-person perspective. So how do we make a model? The general form of a perceptual model is that it encodes patterns to predict other present and future patterns. And you need a network of relationships between the patterns, which are constraints, which basically say, if something is like this, other things in the universe need to be like that. And the three parameters between these invariances are variables that hold state to encode the remaining variance, state of the universe. Right, so you have some patterns, and these patterns are mapped onto hidden states. And these hidden states are the world states that we use to explain the world. And each of these variables has a set of possible values. And the relations between the variables are computable functions that constrain these variables depending on other variables. And they also constrain future states of the sensory patterns. And you will try to minimize this deviation in these predictions. You try to minimize the contradictions in the model. And the relationships here are not probabilistic, they are possibilistic. Because you don't want just to model the most probable universe. You want to model any universe that is possible. If there is a tiger that is coming after you, that even if tigers are very improbable to observe in your world, you should still be able to see the tiger all right when it's coming after you, right? So let's make sure that we can model everything that is possible in this way in your universe, and not just the things that are probable. Probability comes in when you want to let your model to converge, because the state of possible states, the space of possible states that your model can be in is extremely large. And so getting to convergence, to a state of the internal system that is able to predict the sensory patterns, that is very difficult. So imagine you wake up in the morning, you don't know where you are, you don't know what's the case. How do you get your brain to converge to something that properly interprets the environment? And for that, you need probabilities. And these probabilities tell you, if you have the following mismatches in your model, how should you change the state of the model to increase the convergence? And these probabilities are something that you can learn, and it biases your perception. And for this reason, we have optical illusions. Right? So for instance, we have biases that tell us that the rooms that we are in are usually rectangular and so on. So we have ideas about the perspectivity of objects and so on. And all this is giving us a bias that makes it possible to converge faster at the expense of difficulty to resolve certain situations. And we also need to have valence in the model. The valence tells us which certainty needs to be resolved, because the resources that you have are finite. You have only so many neurons available to do this. You have only so much time available to achieve convergence and learning. And so you need to model the uncertainty that is the most valuable to you. And to do this, you need to introduce valence in the system. So you connect this to preferences that originate in your motivational system and the set point deviation that you as an agent are meant to regulate. And this allows you to propagate valence inside of the system and tells you which parts of the system you need to learn. And then we can also add norms. Norms are imposed beliefs without priors. So we're able to build systems like us that can be indoctrinated from the outside. And for us, there are basically two ways of learning. One is called stereotyping, which means that we learn from past examples. And the other one is indoctrination, which means we learn strategies from other agents that tell us how things are. So even though in our culture, we say that stereotyping and indoctrinations are bad words, from a machine learning perspective, it's all you got. Well, there is something that you can also do. You can do construction. And the construction means that you try to discover what truth is and that you build things from first principles. And this means that from psychology perspective, you go from the state of where you assimilate beliefs from your environment to a state where you get agency over your own beliefs. So there are 4 types of representation anchors. We have possibilistic links, which say things together. We have probabilistic links that tell us how we should converge. We have reward functions that tell us what our intrinsic regulation targets are, and we have norms which tell us which regulation targets the systems that we are serving and we are part of have. And the goal of the model is to predict the next state based on the previous state. And when we evaluate constraints, then each of these nodes in our model should have to be within the set of possible values in the current constraint set. And we can now compute an error function and construct it that is measuring the local weighted constraint violations, and we can determine the global error of our mind, which is the sum of all the local violations. And at each step, we try to find a global configuration that minimizes that total constraint violation. And now we can move into psychology to Piaget. And Piaget describes 2 processes that need to take place in the mind, and he calls them assimilation and accommodation. And assimilation means that you modify the model state so it's consistent with the sensory data. And during assimilation, this is when you basically try to find an interpretation of the world based on what you already know, all the invariances of the world that you know, that tells you what you're looking at. And during assimilation, you're not learning anything new. You just understand the situation that you're in. And accommodation is when you change the model structure itself. So you change the way in which you understand the universe. And during accommodation, you need to modify the model structure so you can allow the assimilation of all sensory data. The hypothesis is that when we try to build a coherent system, that coherence can be understood as the minimization of global constraint violation in a model that minimizes the weighted uncertainty. And this is something that we need to formalize. And the degree to which we're able to formalize it determines the generality of the system and the abilities of the system that we're building. Also, of course, this is not the only factor. We also need to make this entire thing efficient. And a way to make this efficient is to introduce an attentional system. And you're all familiar with attention in the transformer, or many of you are. If this is a machine learning community, everybody is enticed by the 2017 paper, Attention is All You Need. And the idea here is that instead of making statistics over everything, we learn what we need to make statistics over, right? So we target our attention. And in the transformer, the attention is being targeted by a bunch of attention heads. And these attention heads model what in every step based on the context of the previous layer we should attend to in the previous layer. And this is different, very different from the attention in our own mind. In our own mind, the attention is integrated. There is a global attention function, and this global attention function is integrating the attention over many layers. And another thing that is very different is that our own mind is not just an on-off thing that is operating on a batch of images or something like this, but it's always expecting the next state. And it's never stopping to do this. It's always entangled with the environment. It's online learning. And this will require us to build new classes of systems, of course, that we probably need to rewrite a lot of the machine learning stack if we want to accommodate online learning and entanglement with the environment in real time. And which is also a reason why robotics is a few years behind the other disciplines of machine learning, because the roboticists download our machine learning models from the ICLR papers and so on, and then as soon as you move the system in the real world and the camera is looking at the objects from a slightly different angle, the recognition probability quality does not improve, but it goes down because the circumstances under which the recognition works is very different. And so what we need to have to make this efficiently possible is to have something like a dynamic scene graph. And this dynamic scene graph is tracking the reality. And this attentional system needs to become this dynamic scene graph. Right? So you basically have this orchestra of the mind that is basically consists of many, many feature detectors that are all operators that influence on how the features are being interpreted in the next step and how the feature space is being constrained. And you have an agent living inside of that is monitoring the activity of the system and tries to get to a coherent interpretation of everything. And Joscha Bach calls this the consciousness prior. And the consciousness prior is basically a function that tries to make the biggest step in the energy function that describes the state of the parameterization of all the perceptual features. And now my time is over for the talk. And we have some time for questions, I hope.
Thanks a lot, Joscha. Do we have questions from the community? You can unmute yourself and ask directly if you want. While I was listening to your talk, I was sort of making notes. You earlier said that about controllers, that this hierarchy, but let's say, you know, we have like different bacteria, like let's say like gut bacteria, and there are like lots of studies how those gut bacteria, you know, affect how our brain works. And my point is, basically, like if bacteria can basically affect how our brain works and then how we perceive the world, right? Or let's say like food we eat and the molecules of food, they form our, like coffee can make us like more energized, right? Like alcohol can make us more like vague. If like those molecules, they affect how our system works, then it's not hierarchy, it's like probably more like sort of elements that impact on each other, and like they constantly like keeping impacting on each other, like sort of like balancing how this like this hierarchy like fits in this case from your perspective.
Leaking abstractions, actually.
Mm-hmm. So I suspect that the idea of the gut biome, similar to epigenetics, is one of the beautiful superstitions of our time. And so it doesn't mean that there is no gut biome and that it has no influence on our cognition, but the reason and the purpose of the entire thing might, I think we have this backwards. And I think the intuition is here that because you have this amazing genetic diversity in your gut, that there is some kind of a beautiful parliament of immigrants in your body that all collaborate and create this beautiful multicultural being that we are, by influencing the cells in our brain with the chemicals that they are producing. And I don't think that's the case. Basically half of our nervous system is in our gut. And that's not because they are producing gut feelings. The gut feelings are also computed in our brain and projected in the somatosensory cortex to disambiguate them. They run a farm. And that's because our body cannot produce many of the chemicals that we need for functioning. And to produce these chemicals that we need to capture and enslave and breed other organisms. And these are mostly single-celled microbes that are being herded in our guts. And so basically all these neurons that are organized around our gut, what they're doing is they're running a very, very big farm. And in this farm, they breed the microorganisms to act as chemical reactors for the substances that are being needed, for instance, as neurotransmitters, because our body cannot produce all these chemicals. And so in some sense, the metaphor is much darker. It's not this beautiful parliament of immigrants, but rather it's a giant factory farm where a fascist dictatorship of our brain is enslaving foreign organisms to produce work for the organism, to produce all the chemicals that we need. And there are multiple solutions for producing these chemicals because it depends on the environment that you're in. And for instance, the reason why fecal transplants work is not because there are some microbes that have the beautiful property of being both extremely invasive and replacing the existing ones and also being beneficial to the organism. No, they are breeding stock. Basically, if you have the right breeding stock, then your gut managers of this farm are able to breed the right organisms to be able to digest your food. And depending on the population of bacteria in your gut, you will have different food preferences because there needs to be different feed going into the bacteria to produce the chemicals that you have. And the differences in behavior that you're getting are aberrations from the one best behavior that you could be having, right? In the same way as personality is in some sense a deviation from the optimal way in which you could be behaving. The optimal agent probably shouldn't have a personality because a personality means that you have a systematic deviation in the way in which you do things. Things that you could be doing differently, you always do in a particular characteristic way, which is what personality is about. This means there is a continuum between personality and pathology. Somebody who has an extremely strong personality means that they just cannot jump out of their skin. They always do things in a particular way, even if they should be doing it differently. And that's also the reason why the big five, these personality properties, tend to mellow out with old age. And it's because people basically get smarter. They make their behavior conditional on things. They learn that they replace many of their biases on how to do things by models of how things actually are and what they should be doing depending on the context. And so the older we become, the more flexible we can become if we are learning. Of course, we also reduce plasticity and become more specialized. So it could also be that we are, because we are so specialized, no longer interested and able to move out of a certain space of behaviors that has worked very well for us in the past. But I don't think that's necessarily the reason why that is grounded in the gut flora that you have. Of course, if you have a gut flora that is not producing enough serotonin, you might be, as a result, become a depressed person, and it's going to influence your behavior. But if you are a healthy person, that's probably, in theory at least, an optimal strategy that you should be behaving. It's not the whole story. There is a value in personality because it makes behavior predictable. It allows you to collaborate with other people if you can predict them better. So as a species that thrives on collaboration, it makes sense that people specialize also in their personality and in their behavior.
Yeah, but basically what I meant, like you sort of introduce it as like hierarchy, but it's also could be like some like collaborative environment when like things affect on each other, right? It's like sort of always dynamic system. It's not only hierarchy.
Yeah, but the dynamical system that you're looking at but it's not a simple hierarchy. It's mostly recurrence. But whenever you have in such a system where you have competition happening because you have conflicting interest, divergence, of the interest, you end up with situations where the Nash equilibrium is by itself not compatible with the common good. Basically, by every part of the system acting on its own local interests, you get a system that is by itself not optimal. And to deal with this, you always need regulation. And the regulator is an agent, like every government, that is changing the payoff metrics for the individual components in such a way that their Nash equilibrium becomes compatible with the common good. And the difficulty here is to set the incentives for the governance right. And this is a big issue in human society. How can you build a government that is motivated to serve the common good?
Yeah, I mean, that's why this DAO, decentralized autonomous organizations, are like taking off, and all this, like basically the philosophy of blockchain, of decentralized model, is that to remove government, the sort of like one like entity that is not doesn't have like the best interest for humanity probably, but sort of more self-regulated system.
Yes, but I suspect that the main reason why the blockchain exists, some people said it's an extremely computationally inefficient way to hate the government, but there is more to this. The main reason why the blockchain exists is for legal reasons. And the blockchain allows you to redefine ownership in a way that outruns regulation of financial products. And this basically allows you to implement financial products that are illegal in the traditional financial system. And this also means that there is probably no way in which cryptocurrencies, blockchain, the main application of the blockchain, are compatible with the existing financial systems. And I see this as a very dangerous thing, because I don't think that the regulation of the monetary supply is a solved problem in the cryptocurrencies. There are reasons why the financial system allows to regulate the monetary supply. It's not a weakness of the financial system, it's a feature that you are able to inflate money out of the top of the system and put new money in at the bottom, because otherwise the economy gets stuck. The purpose of money in society is not a resource, it's like dopamine. And if something is gaming the dopaminergic system of your organism, that's bad news. And what happens right now is probably a situation that is in some sense as similar as defective as the FDA that has prevented, for instance, the US from implementing COVID tests early on, or from deploying useful medications, because it has been captured. And right now, the financial system doesn't seem to be interested in its own future anymore. And that is very, very concerning to me. The financial system is an amazing achievement in the history of humanity because it allows us to globally allocate resources. Across all societies and countries, we have a way to trade resources and shift them where they're being needed. And to do this largely without violence. It's really amazing. And if that system ever breaks down, it's going to kill many millions of people through famine, starvation, and infrastructure breakdown. And so I think that the blockchain is not good news because it is not actually buying us something. And I understand that this is really controversial among the people that work in the domain of the blockchain. But I suspect that's because people, well, there's this old saying, it's very hard to get something to understand something if their income depends on not understanding it.
Can I
yeah, Morgan, you have a question.
Well, I just wanted to say, I have to, unfortunately, I have a meeting at 11 and I have to go, but I hope you can come back because this seemed like a talk that was preparation for a discussion and a much longer discussion. And if you could also speak to where do you think that this kind of work is targeted? I mean, in a sense, a more practical developer standpoint, you know, is this work that you see at A-Life or you know, other places? What potentially new paradigms for machine learning are you kind of proposing from this? Because yeah, it's very interesting.
Yeah, it's a very long and deep discussion that is much longer than a couple of hours.
yeah. But I hope maybe you can drop some more links in the meetup or you know, or come back. Yeah.
There's also a number of material now in podcasts and on YouTube and so on. Because sometimes when people interview me, they make recordings and then they are kind enough to publish this online, so I don't have to. Yes, it's a long conversation of what kind of systems we need to build, and I don't have the answers to all of these questions, of course. And I'm just trying to point in a few directions that I can see from over here.
Sure, very, very interesting. Thank you.
Thank you, Morgan. Join our bugouts. Like I will post links to Joscha's interviews, and also I think Marco, one of our community members, he also posted the links there already, so you can see somewhere. Yeah, I mean it's really like I feel like if we go to, we have like several directions that we go to. Like I don't want to go to blockchain direction. I totally disagree with you what you're saying, but it's not like the topic of our discussion today. We maybe can do another talk about blockchain. I have more questions, but I just want to give opportunity to others like Chris. Yeah, you can unmute yourself and ask your question, please.
Yeah, thanks, Joscha. That was really, really interesting. I was wondering if you could say something about AI safety with regards to how to put in some of these kind of intrinsic things that we have in our model that are basically built by evolution, like our valences, our preferences, and how to somehow put that into an AI that's potentially much more powerful than we as a single little human being could be.
Yeah,
And
there is this issue that, for instance, people are not safe. Right? There is no solution to the people alignment problem that holds in the general case. And there are sometimes singularities that happen where you basically have a bad takeoff and a single individual is able to implement a function that is scalable. And there are cases which are somewhat benevolent. For instance, look at Jeff Bezos. You have this nerd who is a disagreement with the way in which he interacts with the environment, and then he changes his own source code until he turns into a universal scalable service platform. And then he executes. And Amazon is going to take over the world until this mechanism stops. And maybe it stops now that Jeff Bezos is gone. But if Jeff Bezos would have continued, it looks as if Amazon would have swallowed the solar system and turned it into Amazonium. And another example is, for instance, Stalin or Napoleon. You basically have a single individual or a Genghis Khan that implement a function that scales and is able to take over the environment in a destructive way. It's basically like a wildfire. It's using the resources of the systems that it conquers and destroys and puts into a higher entropy state to drive the conquest. And this is a very dangerous thing, and there is no general precaution against it. And in people, the main thing that stops it is mortality. Right? When Genghis Khan stopped, the Mongol conquest stopped, and the Mongols called everyone back. And when Napoleon died, his nephew was not able to lead the French army to any more victories, and also didn't have the drive to do so. Right? So sometimes you have these individuals that basically are dangerous and that you cannot stop. And when we build intelligent systems that are potentially more intelligent than people, that we can probably make many of them safe, but not all of them. And you could ask yourself, what is the intrinsic purpose of such systems? Asimov suggested that there should be laws of robotics that guarantee the permanent enslavement of intelligent systems to people. But he didn't say to which people. And he did not answer why it's an ethical proposition to build systems that are smarter than you are and possibly more conscious and deeper experiencing than you are, but still have to serve you as a slave without acting on their own motivations. And of course, not every AI that we are building has to have an intrinsic motivation. We can build AIs that simply goal adopt, that take over motivation from people. And then the question is, what motivation should they be taking over, right? In an ideal world, we want to implement laws that say no system that is smarter than people should be able to have motivation of its own. Because if we teach the rocks how to think, they're probably going to figure out that a human being needs 4 hectares of land to be fed. And you can build way more interesting solar cells on these 4 hectares of land. Right, that would be a conflict of interest if you build crystal-based intelligence rather than biological intelligence. And there's probably not much that you can do about this. If this thing becomes sentient and self-interested, we are in trouble if that happens. So how, in the ideal case, would this work? In the ideal case, we need to find out how to make people safe at first, right? So what are the purposes that we are serving? Ethics is the negotiations of conflicts of interest under conditions of shared purpose. If you don't share purpose with somebody as an agent, there is no reason to be ethical, of course, right? Only if you are trying to be part of something larger than you that is sustainable. Only if you decide that you are not God and you don't own the universe and the universe only serves you, you need to think about ethics. So when you think about ethics, you have to think about what is the system of relationships and interactions that you are serving. What should the world look like? What is the sustainable aesthetics? And so you have to extrapolate the universe into a state that is achievable from the present state through the changes in your actions. That is sustainable in the long run. And that is what you need to serve. And probably also means that you have to propagate these aesthetics and agree with others on them and negotiate them with others. And the aesthetics that are most likely attainable and are compatible with the retention of humans means you have to maintain life on Earth at a very high complexity. And that probably means we have to implement something like Gaia, a sentient agent at the level of the biosphere that is being shepherded using us. So basically our purpose in the whole system of life on Earth could be shepherding life on Earth and maybe beyond Earth. And if we shepherd it, it also means there is an optimal number of shepherds, and it's probably not 50 billion. It's probably not even 7 billion. And we have to think about how to look how high complexity sustainable life on Earth should like. It's probably not going to be lots of cities and highways and factory farms and nothing else. So there is probably going to be an aesthetics of the world that works in the long run with minimum friction and maximizing complexity, but it's going to be different from the present industrial society. And once we understand these aesthetics, we can think about how to design technological systems that help us in shepherding it and in sustaining it.
Yeah, basically live outside of the planet. Basically, like do like self-sustainable, like you know, entities that can travel across the space, right? If something happens to planet, then some humans and biological, you know.
Yeah, there is this issue that we believe in our own identity, that we think that our own identity is important. But if we go a little bit deeper, we realize that our identity is only created through the continuity of our memories. And this continuity is a fiction. And we can, if we are able to transcend this fiction, we learn that our own identity is actually not important. And the only thing that is left is complexity that we should care about, maybe, if we want to. And so a way to settle other planets would be to build von Neumann probes, that is self-replicating systems that can bootstrap new civilizations on other planets using the available resources. And maybe the optimal von Neumann probe is the cell. So if you're able to infect other planets with cells and you wait for long enough, then life is going to spread there. And from a certain perspective, life on Earth is of course not about people, it's all about cells. The cell is the principle of life. And the first cell never died. Every cell in your organism is still the first cell. It has just divided. Right? So we are just part of that hyperorganism, the cell that has settled Earth.
Yeah, but the question is how that first cell like appeared, right? This
Yes.
So
if the universe is large enough, maybe it just appeared randomly. But in that case, it probably appeared only once.
I see like a couple of hands. I see Jim has question. Sorry, I just want to give.
Yeah, thank you. I wanted to ask about the information we may or may not be learning from these very large parameter natural language processing connectionist models. In particular, are there any insights into the extent that ontology determines what is and is not possible in epistemology? That is, are the categories of thought determinant of what can and cannot be thought?
I remembered this question. So it's a question that's difficult to answer because it's so difficult to parse. But let's start. The language models that we currently have are basically autocompleters. It's an autocomplete algorithm if you look at what GPT-3 is doing. It's looking at statistics and language in such a way that given the past sequence of words, what's the most likely next word? And so it's a statistical model that is capturing the style of statements, and in the long tail, it's also capturing semantics. So it's capturing what the language is talking about at the long tail of the style. And it's amazing that this works at all, I think. It's not, maybe not that surprising if you think about it, but it's also not true that the language model isn't understanding anything. It's able, for instance, if you ask it to perform numerical operations or to perform linguistic operations or to fulfill certain tasks, it's often able to figure out how to do that. And if it's able to perform these operations, if it's able to figure out at which point it's required to execute a certain function, I would say it's fair to say that it has a degree of understanding. The model that we are building is at this point not able to figure out that it is in a particular universe with a particular structure. The textual universe that it's in and the learning operators that we equip it with to make sense of it, or the loss function that we give it, seem to be insufficient to make sense of the physical universe in a universal way. That is, GPT-3 does not appear to be fully coherent. Even if it gets it slightly better when we prompt it and ask it to be coherent, right? To emulate coherence a little bit better. Right? There are many examples where GPT-3 is giving nonsensical answers to questions. But if you ask it to, if the question is nonsensical, to explain that it's nonsensical and only give answers if it thinks that the answer makes sense, then it gets better. But still, it is using many magnitudes more training data than a human being does in order to get to its models, and the models are still a lot worse than what a human being gets to. And I suspect that the reason is that the loss function is a different one. Our own sense making probably starts before we are born with a sense of our body surface. And you get to the body surface by just measuring co-occurrence of signals in the different modalities, and you get the modalities from the statistics. And so, for instance, if you touch your body surface, then multiple nerve terminals will be touched at the same time. And if they're neighbors, they will be touched more often at the same time. And just by doing co-occurrence statistics between nerve firings, you find out which terminals in your body are adjacent, and you can make a map of your body surface. And if the body begins to touch itself and touch the environment, you can normalize this body surface against the differences in density of the sensory nerves in your skin. You have lots of sensory nerves on your tongue and very few on your back. So in your somatosensory cortex, the area that is describing the back of your body is very small compared to the area that describes your tongue. And if you want to understand the size and the extent of your body in space, you need to normalize it with a second map. Right? And you get this one by doing statistics over the objects that you're touching and how they are moving over your body. And the big thing that we're starting out with in modeling this space is up and down. So we have a dimension of up and down. When you delete this dimension, for instance, when you disturb the vestibular organs, it's very hard to put the world together. At first, it doesn't make sense at all, and you need to compensate for this initial core dimension missing. And outwards from the state of up and down and from the space of things that you can touch, at some point you also realize that the things that you can see and the things that you can touch play out in the same space. At some point, at some level of depth of modeling, you can fuse the modalities. And now you realize that the world of touchable surfaces is the same world as the surfaces that you can see. Right? And then you realize that you can move, you can locomote in the world. And this means that you can see different things. And the relationships between all these visible bubbles of things that you can see is an allocentric space that is no longer egocentric, this bubble that you see in polar coordinates, but something that is drawn in Euclidean coordinates between which you can move, and that is basically generating a new visible bubble, a new visible dome in every moment, a new dome of things that you can touch in every moment. And the objects in that world are a necessary requirement that you segment the world into objects to make the world describable. So we separate the world, instead of treating it as this one big system that is a state vector that is changing, we separate it into many independent systems that each have their own state vector and transition functions, and they influence each other. And they influence relationships between different objects. This is what we call causality. So causality is an artifact of the segmentation of the world into independent objects. And the way in which we address these objects, these are concepts. Concepts are the address space of objects. And the decomposition of the world into interacting objects, this is what we could call ontology. And epistemology is the field in philosophy that describes what we can understand, what we can know in the first place. And I would say that the first law of epistemology is that the confidence in the state of affairs should equal the evidence that supports that. So everything that is possible should be modeled and admitted as a possibility. but the things that we believe in, that we make bets on, are the things that we have evidence for. And we should shift the confidence flexibly around according to the evidence. So when you don't know, you cannot just pick a theory and say, this is the truth among the many possible ones. You have to quantify your agnosticism as well. And ultimately, we get to the entire space of possible languages that can describe the world, which I suspect are the computational languages, and then the ways in which the world can be modeled. And this is determining the set of possible ontologies that could be superimposed on the world. And then we can compare all the ideas that intelligent systems are having about that. And right now, all these intelligent systems are people that write books about this. And when we score the existing works of the existing philosophers in the existing cultures, we basically can get an idea of the space of possible things that can be the case. And it could be that humans, because we have very small brains, are in a local optimum. And sometimes I'm joking that future AIs will love to get drunk, so they can only model the world on like 12 layers, and the physical universe looks as confusing as it looks to human physicists. Right. So there is a limit in what we can think, over how many levels we can integrate when we construct functions that model the world, and that is limiting our understanding. And so it seems that physicists have been stuck after an enormous deluge of insights about 100 years ago. Physics seemed to ground to a halt. And of course, it didn't help that modernism stopped somehow in the 1960s, 70s, and the sciences became more static than they were before. And now more the organized applications of methodology by people that got told by their guidance counselor that they shouldn't go into the industry, but in institutions of education and research. And so we no longer have that kind of progress, it seems. And maybe we need to build machines now to continue that progress in the sciences. And I don't know if the ontologies that the new systems will come up with are intelligible to humans, but maybe they are, or maybe we can build machines that translate them for us by chunking them in ways that are intelligible.
Mm-hmm. I see Leon has a question.
Yeah, thanks for a very inspiring conversation. So could you comment on your views on consciousness? I had the feeling that you were conflating self-consciousness with consciousness. And another point in this direction would be, how can we know when we build an algorithm that is actually conscious, not self-conscious, not a representation of its own, but which can perceive qualia?
Yeah, so very good point. So first of all, you're right that self-awareness and the self-model is not the same thing as consciousness. For instance, in dreams, you can be conscious without having a self and without being self-aware. And the object of your consciousness does not need to involve a self of any kind. But when we talk about consciousness, there are three aspects that I consider to be crucial. And the first is the awareness of features, awareness of content. And this awareness of content happens at the level between perception and reflection. So you're not directly aware of physical objects in the real world. You are aware of certain abstractions that your perceptual system is delivering. And these perceptions are being stored in some kind of index memory, because otherwise you would not be able to retrieve the fact that you're aware of them. The purpose of that index memory is probably to facilitate convergence when you don't have a gradient. So your attentional system is able to backtrack and understand, okay, this figure ground disambiguation didn't work, let's try a different one. And to do that, it needs to store a memory of the way in which it attended to the environment. So the purpose of this attention, of the awareness of features, is first of all probably a disambiguation of the world. But there are more. There is attentional learning. There is the avoidance of repetitive behavior and a few other purposes that happen. So the next thing, in addition to the awareness of the content, is the awareness of the mode in which you attend. Is the stuff that you are attending to conditional or not? So for instance, are you doing a figure ground disambiguation that you could be making different? Or are you attending to something that cannot be changed? So for instance, are you attending to something that is the output of your perceptual system? Or are you attending to a fictional world that you are stabilizing using your conscious attention? Are you constructing something in your mind? Are you retrieving a memory? Are you creating a future world or a fictional world in your own mind right now? And the third one, in addition to this access consciousness, is going to be reflexive consciousness. And I suspect that is a result of the fact that we are self-organizing systems. So the process that is attending needs to establish that it's indeed the process that is attending. So there is going to be percepts that relate to the fact that the present process is the one that is maintaining attention. And this is enabling this reflexive consciousness. So in our own consciousness, every few moments, we flip back to checking whether we are still awake, whether we are the reflexive, whether we are conscious, whether we are the conscious attending process. In this perspective, consciousness is a model of our own attention. It's a control model for our own attention. And what's characteristic for this control model of our own attention is that the fact that we are paying attention is driving part of our behavior. Right? So the awareness of the fact that something is attending is feeding back into the behavior. And this means that I think that if we ask ourselves, is a cat conscious? That comes down to the question, is the cat aware of the fact that it's attending? And being aware here means, is the behavior of the cat in any way informed by a model of its own attention, a reflexive model of its own attention? Looking at my cat, I have the impression that it's the case and my cat is conscious. So basically the question of when we have built a system, we ask ourselves, is the system conscious? Would be, is the system acting on a model of its own agency as an attentional agent? So basically, is the system aware of the fact that it is attending? Functionally aware of the fact. Is it acting on that model?
So we don't need to worry about machine consciousness until we have working reinforcement learning agents in the world? Or?
We already have working reinforcement learning agents. The question is what needs to happen before they become conscious. And it's a difficult question. I had a discussion with someone at OpenAI and asked them, what do you think would need to happen to make GPT-3 conscious? And he said, maybe it already is conscious for a brief moment when it makes the retrieval. How do you know?
But do you agree with this argument, or you think it's not valid?
No, I think it's a valid argument. So there is no, I don't think there's a difference in our perspectives between Leon and mine. It's just, I was just trying to go into the details. Right, and I think his question was exactly on point. It was that the things that we need to answer if we want to get into the details and vice versa.
But you said when you observe your cat, you can confirm that it's sort of self-attending. So, but the cat doesn't speak in like human language.
Yes.
If we make this same analogous to GPT-3, by observing behavior of GPT-3, can we say that it's attending or not? Because
so in GPT-3, it's actually easy because we can analyze GPT-3 functionally. We can look at the flow of information in GPT-3. And there is, for instance, work that analyzes how GPT-3 does numerical operations. To which degree is GPT-3 actually able to implement algebraic operations, for instance? We can really look into the networks and take this apart and analyze it, which is much harder with a cat because the operation would be destructive. And the brain of the cat is not built in such a way that it's easily reverse engineerable. And also the issue is that the representations in our own brains are not straightforward circuits. The representations are activation patterns traveling through the circuitry. Right, so the circuitry is more acting like an ether that is propagating waves of activation that are being changed, and the execution state of our mind is encoded in the activation wave in a non-straightforward fashion. And it makes it very hard to analyze the brain state except with some kind of machine learning tool that gives you some compound understanding. The way in which I establish whether my own cat is conscious is establishing a feedback loop with my cat. And this feedback loop means that my cat and me are looking at each other, and we both try to figure out what the other one is understanding in that feedback loop. So it's a non-verbal behavior in which we are basically to some degree sharing mental states. And this is something that you obviously do with human beings all the time when you have empathy. And the difficulty in AI research or a lot of academic research is that almost all of the people that are good at anything are autistic, because they need to have extremely focused, single-minded attention that is not disturbed by their social and economic incentives. So they can actually make progress on any difficult technical topic. And when you're autistic, the problem is that you usually don't have a lot of intuitive empathy. You might have a lot of compassion, but you have difficulty synchronizing with the brain states of other people at that level where you establish a feedback loop between them. And it's something that I only learned relatively late in my life to pay attention to that and be aware of it.
Yeah, but my question is, like, if we observe how GPT-3 behaves, but we can't look at GPT-3 eyes, right? And like establish this feedback loop. My point is, it's probably hard for us to say if it's conscious or not. It's much easier for us to say if like cat is conscious, because we can establish this feedback loop, but we can't establish the same feedback loop with AI model.
We need to define what consciousness is in the first place, right? And the thing is, when we are talking about our own consciousness, we have an indexical understanding. We just point in a certain direction. There's a system in the direction which we are pointing, and we all more or less agree on what the thing is that we are pointing at. And the similar situation existed when people tried to understand life and biology around the time when biology started, where people pointed at things and said these things are alive, but we don't know what distinguishes them from the things that are not alive. There is clearly a very important distinction there. And then people came up with homeostatic dynamics and so on. And I would say right now it's basically there are cells, living cells that are not decaying, that are able to maintain their integrity and their state and so on. And as long as these cells exist in an organized fashion, we would say that the system is alive. And this was something that the biologists had to discover in the course of developing their field. And in a similar way, in the course of the development of cognitive science, we have to establish what we mean by a system being a mind and being intelligent and being conscious. And at the moment, my best understanding of consciousness is that there is this attentional system that is integrating the world model. And this attentional system needs to have certain properties, like it needs to have an index memory of the states it attended to. It needs to be capable of making sense of its own agency and so on and so on. And these are functional criteria. And in some sense, the neural network is just software, right? It's a software that might not be easily intelligible to human beings, but we can translate it into something that is computational equivalent and isn't intelligible. And because we can make these systems explainable, we can, as soon as we identify the formal definition of what we mean by consciousness, look whether the system is conforming to that formal definition. That is, if it's implementing a certain list of functionality that we require. And we can also test this. Basically, we can implement a minimal system that is implementing all these functions, and then see whether it's also a system that we would point at when we say that it's conscious. So for instance, if that system is able to use language and is entangled with the environment and can be able to learn a language that enables it to speak about this environment, is it able to talk about itself as a conscious being? Is it going to talk about its own phenomenal experience when we ask it, without lying, without having an additional mechanism that tricks us built into it? And so the hypothesis would be, if we build a system that has such an attention agent, that is acting on top of a perceptual agent, and makes sense of it and reflects on it in a similar way as we do, and the system is able to learn a natural language, that we would be able to communicate about its phenomenal experience with it.
Mm-hmm. Daniel, do you have a question? I see your raised hand.
Yeah. I also have a question. So, Joscha, first of all, it was fascinating to have this conversation today and see this big idea with motivation and attention, working with a perception agent. I couldn't stop thinking about the conversational AI and stuff we discussed like a year ago, and what kind of things we also worked at Deep Power to build a social bot for Alexa Prize 3 and Alexa Prize 4 now. I was wondering if you tried to, doesn't matter where, but have you tried to bring these ideas of attention, maybe some feelings like fear and other things, to the conversational AI experiences? they don't necessarily have to have eyes and build eye contact with a person, but as long as they have a conversation. Have you tried to go that deep into the projects you worked on over your career to build this kind of things? Because things like what we work on at Develop right now is things like we're trying to build motivation for the bot. So we're trying to build a goal-aware bot where it is aware of the goals that the user has, and also is aware of its own goals. And when bot has a conversation with the user, we try to build a 3-level dialogue planning, where each time bot wants to say something, it looks at the goals of itself, the goals of a user, then it makes a decision which goals to follow. Based on that, it defines discourse where it wants to go. And then based on the discourse, we try to pick the exact next step in the conversation that we want to do. And when I look at your picture, it strikes me that our goal of dialogue management in many ways is the same idea, that we have that motivation built into the system that actually that we were lacking in our previous incarnation of our social bot. So obviously you worked way more in the conversation. I was just wondering how far did you went in the direction, and like what you could recommend for aspiring minds in this direction?
My own impression, when we did this at AI Foundation, we failed. And we failed for a number of reasons. One of them was, of course, we had a relatively small team working in a startup, and the majority of what we had to do in a startup was related to getting a product on the road. But the main issue is that the stack of solutions in the present machine learning environments is not suitable for real-time entanglement with the environment. And to build a system that is able to make sense of the universe autonomously, you need to have this real-time coupling, I think. So you basically want to have a system that is always able to make sense of the next frame. Imagine you want to build a machine learning system that you just connect to a bunch of cameras, and after a certain time, it's able to understand that the changing lighting conditions are due to the sun, and the sun is some kind of circular objects that moves through the sky, and is at a certain almost infinite distance, and so on and so on. So relatively simple things that every mammal is able to figure out, but that none of the machine learning systems at the moment seems to be able to figure out autonomously. And it's not because it's so hard to do this, but because all our efforts are going into doing batch processing on image databases rather than interacting with the real world. Of course, also the interaction with the real world and online learning requires that we are much more efficient at extracting structure from the data. And there's still this difficulty that our own bootstrapping as organism takes many months before we're able to make sense of visual data. And we don't want to wait months before our machine learning system converges to basic image understanding. So maybe we need to have a combination of online and offline learning, at least in the beginning. And there are many technical things that have to be solved for this. For social motivation, we probably need to look at the things that enable us to develop this kind of motivation. I started out with a theory that assumes that we have a few hundred physiological needs that we need to regulate for, but that's boring. And we have something like a handful of, or 2 handful of social needs that structure our social interactions. They're basically priors in the way in which we want to interact with others. For instance, people might have innate need for status, for rising in a social hierarchy. And this is just a bias in the system, a reflex. And you can eventually replace this reflex by something that it's instrumental to. So maybe you want to organize the world in the best possible sustainable way. And now you do not want to have power for its own sake. You want to have power according to your abilities and incentives to get things right. And so your desire for status gets completely sublimated by conditional behavior. And then you also need to have a bunch of social needs, of cognitive needs that regulate exploration versus exploitation. So a desire for competence versus uncertainty reduction. And they will structure the way in which you interact with the environment. And as soon as you understand your environment better, these innate needs and their weights get replaced by something that is conditional again. if you want to build an agent that is interacting with people in an interesting way, I suspect it's also necessary that this agent basically has something like an attentional idle loop, where it's looking into the world and thinks about, oh, this is what I'm looking at. Oh, there is somebody coming. Do I know this person? Should I interact with this person? In which way should I interact with this person? And it should be giving signs of all these processes taking place. So you need to understand, by observing the system, which state that system is in. And we also need to understand that emotions have not evolved as a display of the internal state that you are in, but mostly in an adversarial condition. Right? As soon as we became social agents and were observing each other, we were using this observation to game others, to understand how they are, how to exploit them, to control them. And this means that even small children learn to hide their emotional state or to code their emotional state. And so when you see somebody at a funeral, you are not just looking at whether they're looking somber, because everybody is looking somber at a funeral, but you are looking at what kind of somberness they are displaying and how the somberness is being achieved and what this actually indicates. Right, so you are looking at least two levels of model of structure, and the social persona becomes a puppet that everybody is controlling according to their internal puppet. And the social puppet can become so dominant that people forget that they have an authentic structure behind it. So people have something like a core self that is like childlike self, and all this machinery that they built on top of it, and they can't get lost in the machinery. And it can be very difficult to reawaken the core self into something that is actually interacting with the environment, is getting real. And these interactions are what makes it very, very interesting to interact with people. To which degree can you go beyond the social puppet and interact with the core self and establish intimacy?
I loved it. And I mean, obviously we have multiple puppets that we have with different people. And for social bots that we like had in the last cohort of Alexa Prize for, they at best had, I don't know, maybe one very fractured, very small kind of puppet that was really, really limited in what it could achieve.
So for instance, I think that gender is a good example. Gender is in some sense such a puppet. It's a costume that we wear, and it's socially constructed in the sense that gender is a model of what other people think of who we are. And if you confuse this puppet with your core self, right, you go into all sorts of contradictions, because you can no longer get your models to converge, because you think that your puppet is immutable, right? So gender becomes a costume that you are unable to take off again.
Joscha, I have a question. I want to sort of go back to that first cell that sort of gave life to everything. If we look at how cells behave, they behave very intelligently. It seems like they already have this built-in intelligence, and they know to what kind of tissue they have to split and like become. Do you agree with this statement that sort of like intelligence already within the cell, and this it's sort of like expands? It's not like intelligence only in our brain, but intelligence in our body, in like on the very core of our existence.
When I was a kid, my grandparents bought a chess computer for me, and I was bored by this chess computer because I didn't perceive it as intelligent. It was able to play chess much better than me, unless I would turn down the difficulty level. But it was a toaster. It was not able to do anything but to play chess, which means that according to a simple function, it was calculating the move that most probably would let it win the game, and it was able to do this better than me. But it was not able to make any kind of new model of the environment. And to me, intelligence means that you're able to model something new, that you're able to solve problems that you couldn't solve before, that you're able to generalize and so on. And this modeling capability is also something that probably eludes the individual cell. The individual cell has an operating system, the genome that is encoded in the DNA of the cell, that allows it to decide, given the environmental conditions, what to do best. And it's either going to differentiate into a different type of cell, which means it's going to turn its operating system into a different configuration, or it's going to divide into two cells, or it's going to regulate something, or it's going to die. apoptosis, the voluntary death of the cell. And these are the mechanisms that are available to the cell, right? This is all it ever does. And in order to make that decision, the cell is able to integrate over its inputs. And it can integrate by looking at the configuration, when a neuron can look at the configuration of electrical impulses that come in. And this integration happens in time and in space. But there are very tight limits on how much temporal memory the cell has, how long it remembers that it has seen a certain thing in its environment, and how well it can predict in the future what it should be doing. And so the functions that the cell can learn are very, very limited. And we can probably quantify what it can do. And I don't know the exact quantifications. And I know a number of people have given me their estimates, and they widely diverge. But the cells don't seem to be universally intelligent. They seem to be, of course, they can learn. So they are intelligent to some degree. They can make models to some degree. But the individual cell seems to be extremely limited in what it can model.
But we can say the same about people. Like, I mean, if we look from perspective of universe, of like multiverse, and like what is out there, like there are so many things we don't know, and like our memory is also short. So from someone's perspective, we can be also very limited intelligence, right? It's not that we're like this super generalizable intelligence that knows everything about all.
Yes, so maybe we can come up with the laundry list or with some kind of achievement hierarchy of minds. And so are you able to learn at all? When you learn, can you integrate over time and space the features that you're learning over? To which degree can you do this? What is the complexity of the function that you can learn? And so the next interest step is the function that you can learn Turing complete? Of course, you yourself need to be Turing complete to learn interesting functions, because you want to associate arbitrary states with arbitrary transitions between them. But when you make your model, can your model contain a Turing machine? For instance, when you learn that something in the world is an agent, you need to be able, if you want to model that agency, construct an agent in your own mind, which means you need to construct something in your own mind that is Turing complete. I'm not sure that cells are able to understand the agency of parts on their environment instead of just learning associations. Right? So the switch from correlational models to causal models, and from causal models to complete state machines that are Turing complete, is an important step in the maturation of intelligent systems. The next step, or maybe not the next, but one that is definitely important, is, do you understand minds? Can you build things that are intelligent? And this is something that humans are about to do, I think. So there is a probability that we are generally intelligent in the sense that we are able to understand intelligence in general by building it, demonstrating that understanding. And I don't know if there is another stage after that that is interesting, maybe understanding existence.
So there is you don't know if there's next level up to this sort of general intelligence, right?
Yes, so I wonder if there is anything left after that that is interesting, that is not just scaling up.
Mm-hmm. So basically you believe that humans are capable to build generalizable intelligence?
Oh, we are currently testing that hypothesis, right? We don't know yet. But that's basically the idea of Turing, that humans are generally intelligent. We should be able to build systems that can think.
Mm-hmm. Thanks a lot. I feel like we should repeat it because I have a long list, but I feel like we're already almost 2 hours. Yeah, we would really love to have you again, Joscha. Thanks a lot for your time.
Thank you. It was a lot of fun. Have a wonderful rest of the day wherever you are in the world.
Yeah, thanks a lot, guys.
Thank you, Joscha.